Okay, so welcome back to the first episode of the second season of the Python People podcast, the home for global technology leaders to share insights with the tech community. And this week we're kicking off with a bang with a guest that I've been quite fervently trying to get on the show for a while now, and thankfully our diaries have finally aligned, and we've managed to make it happen. So a very warm welcome to Alexey Morgunov. Alexey, thank you very much for being here with us today.
Thank you for having me.
No worries, absolute pleasure. So Alexey, you are the head of machine learning for Fluid Analytics. And I guess to frame the conversation a little bit today, so you're someone who's got, I'm sure we'll hear a little bit more, but an incredibly rich and accomplished background in research and biotech in particular. And I suppose the world we're all living in now, biotechnology and certain facets of it, like drug discovery, have become very much on people's radar over the course of the last couple of years with the pandemic. And I think it's now more poignant than ever before. But in our very first chat, we got speaking about the link and the relationship, or the role of data science within biotech, and sort of how those two intertwine. So we thought it'd be great to get together, share a few ideas, and hear a little bit more about some of the really interesting work that you're doing at Fluid Analytics. So I suppose before we delve in, I'd like to start where I always do, and invite you to, if I may, just tell us a little bit about yourself and your impressive academic and professional career to date.
Well, thank you. I guess my story begins with an interest in molecular biology, and especially synthetic biology. So I had nothing to do with coding, Python, data science, machine learning, nothing like that at the start. So I was pretty much a wet lab scientist, interested in engineering proteins, engineering nucleic acid systems like ribosomes, and I studied molecular biology and then switched to systems biology. Now, it was during that master's course in systems biology that I started to discover that biology has matured enough that data approaches, and especially computational approaches and modeling, can finally be used to answer biological questions more rigorously than it was done previously. So during my PhD, which I had already decided by that time that I'm going to start in a wet lab setting, I actually switched entirely to computational work just after a year into my PhD. That was a difficult transition, but I don't regret that at all, because I realized that I can actually now finally start answering questions in biology using computational means. And this is when I learned to code, took up machine learning, and never looked back. I haven't held a pipette in my hand since my first year of PhD, and it's been quite a long time since then now. So after my PhD, I went into consulting for a short time. I started a consulting company focusing on machine learning in R&D specifically, solving hard problems. And then eventually I ended up joining one of our former clients. So Fluid Analytics, I started working with them originally through that consultancy, and then they invited me to lead a machine learning team internally. So this is where I've been for the past now over a year and a half, building a team of data scientists and machine learning engineers and scientists. And it's been a fascinating journey, because I think, as you said, biotech today is the place to be in many ways than one, but especially when you're bringing together computational approaches, the new developments in data science and machine learning, and you're trying to apply those to solving problems in molecular biology. That's a really fascinating place, and I'm enjoying myself there very much. I think had I stayed in wet lab world, I think I would have found really interesting problems to work on, but I'm really glad that I made the switch.
Yeah, fantastic. What a great story. And that's why I really love data science and kind of working in this industry, because it's always really interesting to hear how, I guess data science in the way we know it, statistics and computer software engineering obviously has been around for a long time, but data science and the guys that we know about space are still a relatively modern entity in the technology world. And I'm always really interested to hear how people arrive into the world of data science. And, I think there's a lot of really interesting examples of how people have worked out, like say the kind of the level of maturity that exists now, how that can be applied to certain industries to really add a huge amount of value and solve a lot of real world problems. And it sounds like you've very much hit that sweet spot and found your calling and your passion. So that's always great to hear. So So talk us through then a little bit in your experience about how data science can be applied to molecular sciences to, you know, really add a lot of value and advance those processes.
Right. Well, I think, it's fascinating to think about biology and where it is today, really. In a post-genomic era, we really talk about humongous amounts of data. We used to say, I think, that there are astronomical amounts of data, referring to astronomy as the science that generates the most data. But I think we should replace that with calling it biological amounts of data, because really today, with all the new techniques, from DNA sequencing to proteomics, with the amounts of data that we're able to generate about biological systems is just outpacing our ability to properly analyze it or to come up with methods to really integrate that knowledge and generate insights from it. So I think one key thing that has changed in biology and why data science is becoming relevant is because we now have the means to interrogate biological systems at many scales and with throughput that generates data which is now sufficient to start. Well, I don't want to say sufficient, because you can always do better, but it's good enough to start making forays into modeling approaches that actually have predictive power, explanatory power, and so on. So I think, for me, applications of data science and molecular sciences especially are interesting where it has to do with learning about the function of key biological molecules like proteins. I'm very much deep kind of in the biochemical world rather than cellular world. I could talk a lot about how machine learning data science is applied at that scale as well, but whatever scale in biology you look, there is plenty of machine learning and data science being applied. But for me, the really interesting areas, and especially some of the newest developments, are happening on the molecular scale. And that's where fluidic analytics sits as well. We look at protein-protein interactions and modeling how proteins are structured, formed, expressed, how they interact, how they perform their function. That's something where data science has recently made significant advances. And that's really been down to two things. I already mentioned the data, but I think to add to that, data is not just about the amounts of it, it's also about understanding how to extract knowledge from it. And so we're learning how to debias biological data sets better and better, how to incorporate inductive bias from biological entities into how we architect models and how we build actually the machine learning approaches to analyze that data. And on the other hand, we're learning about how to represent biological entities better and better. So I would say if you can debias your data and you can figure out a way how to encode it as a vector of numbers, then what you do after is no longer as difficult. So biology today is no longer about just taking methods out of natural language processing or computer vision and just applying them to biological entities, but it's about trying to figure out how to use specific approaches for biological entities themselves. And that's what I find the most fascinating about data science and molecular science, where they converge.
Yeah, absolutely. Yeah, I think that's a really interesting point, like you say, because in so many industries, obviously, data is being created at such a unbelievable rate, but it's now about the sophistication, I guess, of the practices of how we approach that data to extract the value. And yeah, I can fully appreciate that. And I guess on that note, then, within, like say you talked about the predictive capability, explanatory capability of a lot of the approaches that exist today, what applications of machine learning have you come across that you're kind of most excited about within the world of biotech?
Well, I guess everybody has heard of AlphaFold and their success recently. DeepMind solved the problem of going from a sequence of amino acids to predicting a stably folded structure of a protein domain. It's not quite the protein folding problem. There is more aspects to the protein folding problem. Therefore, I haven't referred to it as solving the protein folding problem. But it is a pretty important step in our understanding of the biophysical properties that govern protein structure and function. And I think there's a lot of excitement at the moment around this space. So now that we've achieved such an important advancement that people have been working on for the past 60 years, trying to do. And Finzen's dogma was formulated in 1961, stating that protein structure should be encoded in a protein sequence. Now that we've proven that we can actually extract that information, the exciting world opens of what can we do with it. Does it allow us to engineer proteins better? Almost certainly yes. Does it allow us to design proteins, more sophisticated protein-based machines? Almost certainly yes. And in the next few years, we're really going to see this knowledge being put into practice. Now, we no longer work with a limited number of protein structures. Now, every folded protein domain in any organism, we now have a pretty good idea of what its structure is. So suddenly, the baseline knowledge about proteins has shifted from a sequence to a structure. Now, that is a step change that we're still trying to understand. So I think, for me, really, the excitement is about how do we adapt to this new world where structure becomes the basic entity, and how we start thinking in a different way and start thinking in a structural way about biological entities. And I think this is where it becomes important to consider the functional context in particular. So proteins, they don't exist in isolation. They exist in the cellular environments. They perform their function typically through interactions, and therefore it is focusing on those functional aspects more and more that is going to help us drive this science forward.
Yeah, wow. I mean, I guess with such a kind of a fundamental advance that's been made forward, I mean, that must open a ridiculously exciting world of possibilities in front of you. And I guess it's sort of knowing how to focus that, how to kind of harness that into the real world, isn't it? And it's always this this paradigm. I have conversation quite regularly about machine learning and data science. It's obviously still very much the hot potato and the buzzword in lots of companies, but in reality, I guess it's difference between sort of difference between commerce and biotech and those sort of science-based industries. But generally speaking, a lot of the work that happens, machine learning can't sort of exist in a vacuum and sort of just answer that question unless there is an actual real world application, for that problem being answered, and a way to provide value for mankind, I guess. And you're somebody that's obviously done a huge amount of work in this research and development space. How do you see those sort of two entities interacting between kind of the research side of it and making these huge advances forward in terms of what's just happened, but then how do you then extrapolate that out to providing real world value, and how do you go about sort of that process of understanding which problems to tackle first?
Well, I think first and foremost, these advances really accelerate our ability to translate advancements in biotechnology into something applicable. So I think the more we aim to replace experimentation with computation in biology, the faster so that this design, build, test cycle is going to become. I think biology is maturing to become an engineering discipline gradually. We're not quite there yet, a lot still to be done, but we are getting there. The age of biology as an engineering discipline is almost upon us. And that's where we're really going to see it turning into applications quicker and quicker, because we'll just be able to iterate through what we come up with, what we're then able to test, and what we're able to then improve and test again. And we're going to be able to iterate through that cycle a lot faster, with machine learning being part of that loop and an important player in that loop. So I really think these fundamental advances are really setting the basis for real-world applications of biotechnology, all the way, from drug design, structural understanding of proteins that I talked before. That's really important for being able to figure out how to drug those proteins, how to design small molecules that bind to those proteins and maybe disrupt their interactions, and so on. Protein engineering, we have so many industrial applications of protein engineering, from food industry to potentially even solving problems like plastic pollution in the oceans. We really do need biology everywhere we look, from medicine to environmental sciences, and these advances are all going to be accelerated through our ability to integrate computational methods as part of the pipeline. So I wouldn't say that in themselves computational methods are a panacea for biotechnology, but it's about the ability to figure out how to effectively integrate them into what we've been doing before to help do that better and faster. That's what's going to change.
Yeah, fascinating. And I guess on that note, you mentioned a couple of examples there, sort of pollution in the oceans, etc. But do you, and I totally agree, yeah, I really like that concept of biology being ushered towards an engineering kind of discipline. I can totally see the logic for that. But do you see in all of your work any kind of obvious parallels or crossovers between the focus that you have in biotech and how data science can be applied there, and how that can actually sort of cross over to other industries?
That's a really good question. I think there are obviously many parallels with pharmaceuticals, pharmaceutical discovery, which is more traditional chemistry, and very much similar approaches can be used there, also accelerating the discovery pipeline. But if you branch out further than material sciences, again, similar approaches to describing the molecular space can be helpful in discovery of new semiconductor technology, new materials, and so on. But even broader, I would say environmental sciences is a big one, because we think of biological entities as these complex interconnected things that are very difficult to describe, which are chaotic on the inside. Whatever end of them you poke, the changes revibrate through the entire system. And I think our planet is very much the same. And the problem is that we are actually poking our planet way too much from all sorts of directions, and actually figuring out how to reverse that process, how to reverse climate change, how to reverse pollution, how to live more sustainably on this piece of rock. Now, that's where I think modeling approaches, data science, and relying on large amounts of data that we're able to collect on a planetary scale, that's going to mirror the challenges that we tackle in biology. We're going to have to build complicated integrated models. We're going to have to make sure that machine learning is very much part of this, and helps us create solutions to these problems, to change everything, from our supply chains to maybe even all the way to doing geoengineering on a planetary scale in order to reduce the impact of climate change. We cannot be just carbon neutral in order to reverse the damage that's already done. We actually have to proactively do something. But how to do that in an informed manner, I think that's where approach is very similar to what we apply to understanding biological entities are going to come in.
Yeah, absolutely fascinating. And I guess when I think about the kind of bigger questions to do with climate change and that sort of things, I think it's obviously fascinating to understand how the advances that can be made through the likes of data science in terms of predictive analytics. And I think it's really important. Like, great point about being able to reverse that, and because as much as you can have the solution mathematically, and you can sort of actually, and we're getting to that point now, like, so I think we do have that level of sophistication in our data practices where we can actually almost answer quite a few of these questions about what we do need to do. It then creates that sort of juxtaposition between the maths and the right solution and having the answer, and actually the curving of human behavior, because I think a lot of it actually is not so much necessarily around the answers from a mathematical standpoint. It's actually about being able to get people to understand the impact and change those practices, because we are in the state we're in, quite frankly, because of human behavior. And whenever I think about all the advances that are kind of being made in climate tech and that kind of thing, very often it's really inspiring to see, but I always still have a large degree of apathy of thinking that that unfortunately the masses, the majority of people, we wouldn't be in this situation if most people just did a little bit of something different. But it's actually changing that behavior at a fundamental level, which is kind of where
Yeah, absolutely. Incentive engineering, sort of social engineering, where we actually push and prod people to do the right thing by creating the right economic or social incentives, and maybe a better ability to model those interacting systems, our economy, our social behavior. Maybe that's something where data science can help as well. It's a bit too far from the domains I understand, but I see that as being yet another interconnected system where maybe we can make a difference. But again, you have examples. Cambridge Analytica, right? An infamous example where machine learning has proven itself to be capable of social engineering, just not for the right purpose, arguably.
Yeah. Yeah, absolutely. Yeah, very true. Hopefully the same force can be harnessed for good. But no, it's really interesting. It's kind of it's a real, like say, interconnected paradigm, isn't it, of how these things interplay with each other. But no, that's absolutely fascinating so far. And I'm really interested to hear a little bit more about how you go about approaching. You mentioned building out a team of data scientists. How you go about approaching your projects within data science. But I think it's fair to say the kind of work you're doing is probably very different in many ways to, building a predictive model for, food delivery and delivery, for instance, in terms of, there's obviously quite a big difference there. So in terms of the projects that you're executing, how do you have specific methodologies that you employ when it comes to how you go about your data science projects?
I think I should start with telling a bit of a story of data science at my company, because that would help contextualize and help answer this specific question. We actually started off as a company that produces instruments for a specific application, measuring protein-protein interactions in solution against complex backgrounds. So that's something that we viewed as a black box. You put it in front of a customer, and customer does experiments with that. Quite quickly, though, we realized that that's not all. We really do need to create a platform and ecosystem around it, and that's where data comes in. These instruments, they generate data, a pretty unique type of data that characterizes these biological systems, and there's a lot of value in analyzing this data, coming up with approaches, that predictive and modeling approaches around this data ecosystem and these experiments. So the data strategy was added on later onto the business model of the company. And that's what creates both some opportunities and some problems for me in particular. I came into the company first as a consultant, as I mentioned, to help come up with the data strategy, to design what it is that we can do with our data, how it can integrate into this ecosystem, and really figure out what's the value add we can create in the longer term and what kind of research we need to do for it. So this means that I faced the challenge of at the same time kind of integrating data science into already a relatively mature system. There is R&D of the instruments itself, there is production, there is customer support and how it's being rolled out to the customers. All of this process is devoid of really data solutions, data applications, and value creation around data. So we need to figure out how to create value add there. And therefore also the kind of team that we create, it needs to work across many different levels of support of this ecosystem. So I would normally split my team into two. One which works very closely exactly with the data that the instruments generate, creates analytical tools that are rolled out to customers through our cloud infrastructure to help analyze experiments performed on the instruments. And then the second half of my team is more about longer term strategy, about research and development into questions that help support the overall ecosystem longer term. And it's about kind of creating the right balance between these two, and how we gradually go from R&D and figuring out solutions to difficult problems, and gradually advancing them towards implementations already in something that's more production level of what's actually reaching the customers. So in creating this kind of team, I have to think about quite a diverse range of expertise as well. On the one hand, we're doing software development, a very kind of traditional kind of software development. So methodologies like Agile are our bread and butter, and we have to think in terms of delivering a particular product. We have to think in terms of pretty constrained goals and milestones that we understand, because this is already around implementing solutions that we have previously developed. But on the other end of the spectrum, we're actually running almost a small academic research group where we're tackling challenges not different at all from what people in academia would be trying to tackle. We are exploring, we're trying to find our footing in entirely new areas and try to capture that value early on, in order to know what to bring into our ecosystem as a product.
Fantastic. I mean, that's a great answer to. I mean, it seems like you've got a really all-encompassing approach to how you integrate. I have a conversation quite regularly with data science leaders where, because data science is this kind of shiny new object. A lot of companies are like, hang on a minute, we need to go and build a data science team. We're not too sure why yet, but we need to go and build one. And then they'll hire a really experienced, quality data leader to come in, and there's just not that awareness, I suppose, or appreciation really for why they need it from the top down. If they're kind of expecting all the answers to come from the bottom up, and that whole situation of how you integrate data science into a business where a lot of the processes are sort of set in concrete already, and how do you go about actually demonstrating that value. And a lot of it really is about, so going back to the point we were talking about, social engineering, but sort of a lot of it's winning hearts and minds, isn't it, and getting people to change their behavior,
right.
Appreciate the value that's being demonstrated. And it sounds like your approach there is working at sort of lots of different levels to kind of fundamentally make that work from different angles. Yeah. So fantastic. I mean, I guess going on to you mentioned that the types of what you're doing there varies from kind of more classical software engineering to some of the more advanced analytics side of things. But when you hire for a data scientist to come into your team, what traits do you feel are really important traits within a quality data scientist?
So I think I would specifically focus on answering this question with regards to data scientist or machine learning researcher, as opposed to more engineering or software development role, because I think those are kind of better understood. So I think your question is more about the data scientist side and more researcher side. There, I'm looking for a person who is quite attentive to detail, first and foremost, because I think it's very important when you are sifting through large amounts of data, trying to understand what it is that you're looking at, trying to understand the bias, trying to figure out what approaches work better than others. You notice the little things. You're not happy when there is this one point that just sticks out, right? It could be the all-important thing you haven't taken into account. You do want to care about such things. You need to be meticulous enough to worry about it and want to make sure that everything falls in line. You also need to be attentive enough to notice those things in the first place. You need to have a research mindset, I think, quite importantly. You need to be able to kind of iterate through creating hypotheses, testing them, going back to the drawing board, figuring out what it is that you don't know, kind of evaluating your assumptions, so quite self-reflective approach on the process. I think people who come out of PhD quite recently, they almost always have at least the beginnings of such an approach, and this is why I quite like to kind of hire people with academic backgrounds into this role, because they have that's kind of trained into them during PhD, where you're facing quite open-ended problems. I think that works quite well in data science, even though you might be working on something where sort of the process is understood. Being able to improve that process only comes from that kind of insight, from the attentiveness to detail and the research-focused mindset. So I think I focus on that even more than I focus on specific experience and specific familiarity with tools that you can pick up. If you're an intelligent person, you're going to learn that, and there is so much online in terms of resources from which to learn these things. And when we code from Stack Overflow anyway, not from our own memory. So that's the kind of reality. You need to think in the right way, and then you're going to be able to figure out what it is that you need to do. Because actually finding a person with the right experience for very domain-specific jobs is really hard. It's quite unlikely that you're going to find a person who has done exactly the kind of thing you are doing. They will have to learn on the job anyway. So it's better instead, if you're looking for something extra, to actually focus on specific domain expertise. So in our case, if we're working in protein science with proteins as objects, somebody who has done experimental work on proteins, or maybe computational modeling work, bioinformatics with regards to proteins, that's the kind of background knowledge that we find useful. You never know how exactly it's going to come up. And maybe they've done something entirely unrelated, but there is knowledge that's going to somehow propagate to what they are going to be doing with us, and that's going to be quite important for them to be able to have a baseline on which to build, and that kind of background, almost lexical knowledge that helps them notice the right things.
Yeah, absolutely. Yeah, I think that's a really refreshing and really pragmatic approach to take, and I think I can certainly understand your point there about certainly any knowledge of domain in your particular niche, I'm sure would be very advantageous. But it's really refreshing to hear that. I was speaking to a client the other day who had a role profile, and they listed under the essential experience 10 different machine learning libraries, and said that they need to have commercial experience of these 10 different machine learning libraries. And I'm sort of asking the question of like, why do they need to have that? It's, for a start of, most companies aren't really executing machine learning in a particularly effective way, and even if they are, they're probably working with maybe 2 or 3 of those libraries. So to try and find somebody that's gone out there, and just companies that I think are focusing too much specifically on the tech and not so much around, like you said, the mindset and the curiosity, that sort of approach. I think the attitude is obviously, of course, you need to be able to have, like I said, attention for detail and have the kind of mathematical and computational kind of mindset. But I think the curiosity side of it and understanding the question is just as important, if not more important, in the world of data science, in my opinion, than it is somebody that's gone out there and put 50 different buzzwords on their CV. So it's great to hear that you're sort of a similar mindset.
But those buzzwords, they may come in important when you're actually trying to productionize something. So familiarity with specific toolkits or specific stacks of different libraries, that might be quite important. But that's already more in the domain of engineering and more in the domain of software development, in my mind. And you always need to pair good researchers in data science with good software developers, because those skill sets are often actually quite separate, that you find them in different people. So when somebody hacks together, really, hacks together a solution that just about works, then you need to sit down with somebody who knows how to actually make that work reliably 99.9% of the time, how to build a product almost around it, how to integrate it into the stack of what we already have, and so on. And that's when those buzzwords become more important. So it's a different kind of domain almost in which we're looking for people.
Yeah, totally. I totally agree with that. And I think obviously there's such complex problems, and like you say, that from the research end of the spectrum to the productization end of the spectrum, obviously 2 quite different skill sets. And of course, it's very important to have complementary offerings and skills within the team. Other than the team itself, are there any wider business factors that you feel are really important to consider? Coming from somebody that's integrated a data science function from scratch into a relatively established process business, are there any kind of other important factors you feel are important to consider to ensure success of data science functions within a business?
Communication, I would say, is the main one. You really need to make sure you explain what it is that you're trying to do in a way that other stakeholders understand. You need to show to them that you're part of value creation and that you are helping and supporting them in that process, rather you being the fancy, shiny add-on. It's not a bell and whistle onto an existing system. It's an integral part of the system. And creating that understanding, and kind of showing how what you're building is able to solve problems, improve processes, and actually help others, I think that's really key. When you're integrating data science into an existing business, or even when you're building it all from scratch, you really need to think about how it solves a particular person's problem. Other stakeholders, as part of this, they need to see that you actually removed some pain points for them. Then data science can be an active part of the business rather than being seen as something siloed off and working on fancy things that only investors see the value of and increase valuation of the company. That's not the case. Data science is a real part of the entire process, and other people benefit from it within the company as well.
Yeah, I think that's a great point. Because with a lot of conversations we have with sort of early stage tech businesses, when they're talking about speaking to investors, it's usually one of the biggest questions is, what's your AI strategy? Where's your data science team? And fundamentally, the businesses that really succeed are those that understand why they have it, and actually that the value is seen internally, and it is a really well respected, usually very central function within a business, because it's really integrated well and sort of demonstrated that value to the internal stakeholders within the business. So yeah, I totally agree with that. Fantastic. Well, Alexey, it's been a really really interesting chat, and a real privilege to speak to you. So thanks very much for your time, and very exciting work that you guys are doing over there at Fluid Analytics. So keep up the good work, and I'm sure there's many breakthroughs to be made, and a lot of advances that certainly will come out of the pioneering work that you guys are doing there. So yeah, I wish you all the best of luck with it moving forward, and yeah, pop back on again if you'd be so kind in the future, and let us know about your latest breakthroughs, and hopefully we can get together and have another chat again at some point in the future.
Thank you very much for having me. It's been a pleasure.
Take care. Speak soon. Bye for now.
Bye.